In this lesson, we will acquire and validate our first measurement from an NI DAQ device. Consider a scenario where you're conducting experiments on the growth rate of plants in different environmental conditions. You need to collect and track data such as temperature changes, humidity, and soil acidity. Where would you begin creating an application to acquire this information? Data acquisition is the process of measuring an electrical or physical phenomenon with a computer. By using NI DAQ systems and LabVIEW, you can customize all aspects of data collection. A DAQ system consists of a sensor, an NI DAQ device, and a computer. You choose the sensors you need based on your application. Different sensors measure different phenomena. Depending on the type of sensors, its electrical output can be voltage, current, resistance, or another electrical attribute that varies over time. For example, to measure pH, you would use a pH probe connected to a DAQ device that can read the voltage values that the pH probe produces. To measure temperature, you could use a thermocouple, which produces a voltage that varies based on temperature. With the thermocouple, you can measure a voltage and use a formula to convert the voltage measurement to temperature. NI DAQ devices come in different form factors, from NI compact DAQ systems to multifunction DAQ boards, such as the X-Series DAQ board. You select different NI DAQ devices based on the complexity of your application and performance requirements. LabVIEW running on a computer can acquire these signals from the DAQ device, analyze them, and present the results. You can group real-world signals as either analog signals or digital signals. Analog signals are signals that vary continuously and have continuous values. Examples of analog signals are temperature or current. Digital signals are signals that transfer binary data, on and off, high and low. Let's take a look at some examples of analog input. This analog input example acquires a value from a thermocouple sensor at a relatively slow rate of 2 samples per second. This analog input example acquires a high-frequency voltage signal at a much faster rate of 1,000 samples per second. Other analog input examples include acquiring signals from accelerometer sensors, strain gauge sensors, microphones, current signals, and more. Analog output describes generating analog signals from your computer and NI hardware. To perform a voltage or current output, a compatible device must be installed that can generate that type of signal. Let's take a look at some examples of analog output. This analog output example outputs a voltage ramp to control the speed of a fan. As the voltage increases, the fan speed increases. As the voltage decreases, the fan speed also decreases. Another analog output example would be to output a stimulus signal to a unit under test. For example, you might need to send a sine wave, square wave, or triangle wave with specific amplitude and frequency to your unit under test to investigate how the unit under test responds. Digital input describes measuring a digital signal and transferring the measurement to a computer for analysis, display, or storage. Let's take a look at some examples of digital input. This digital input example reads the status of a physical button or device. For example, if the digital signal has a low voltage, that could mean that the physical button is not pressed. And if the digital signal has a high voltage, that could mean that the physical button is currently pressed down. This digital input example shows that your application could wait to receive a start trigger from an external digital signal before your application starts a task like acquiring data. This digital input example reads a digital protocol signal where a high voltage represents a binary 1 and a low voltage represents a binary 0. Digital output describes generating digital signals from your computer and NI hardware. Let's take a look at some examples of digital output. The first digital output example outputs a digital signal to turn on an LED or another device. The second digital output example outputs a trigger signal to trigger another device to do something. The third digital output example generates and sends a digital protocol signal. This course will use mostly analog input measurements for examples. Before connecting your hardware, make sure you install LabVIEW and the NI DAQ driver. Then, refer to the user manual for your DAQ device for detailed instructions on how to connect your NI DAQ hardware to your computer. For example, I have this CDAQ 9178 compact DAQ device that contains multiple C-Series modules. And I can connect it to my computer using a USB cable. We can configure and test our device with Measurement and Automation Explorer, or MAX. MAX is used to do the following: configure your National Instruments hardware and software, backup or replicate configuration data, create and edit channels, tasks, interfaces, scales, and virtual instruments, execute system diagnostics, view devices and instruments connected to your system, and update your National Instruments software. We can simulate NI DAQ devices using MAX as well. Using simulated NI DAQ devices, we can try NI products in our application without the hardware. Now I need to connect my DAQ device to the sensors and signals that I want to measure. In MAX, I can find guidance on this by viewing the pinout, manual, and specifications for the device. To do this, I need to navigate to Devices and Interfaces, where I can see all the hardware connected to my computer. I can click on my device, and now I can view the pinout diagram, so this can help me make the physical connections. Lastly, you can also view the manual and specifications for this device by clicking these buttons. The next step is to acquire signals. But before we acquire a signal, let's make sure that we understand the fundamentals of choosing the correct sampling rate for an analog input signal. Sample rate is the rate at which the DAQ device acquires a sample on each channel. For this example, this analog input channel is acquiring at a rate of 10 samples per second, or 10 Hertz. Now let's take a look at how to choose the correct sample rate based on the signal you're trying to acquire. Here we see that the signal that we are trying to acquire is a sine wave that has a frequency of 100 Hertz. This means that the sine shape repeats 100 times per second. If you set your NI DAQ device's sample rate to 100 Hertz, the same frequency as your actual signal, your acquired signal for this example will look like a straight line, which does not accurately represent the actual signal. If you set your NI DAQ device's sample rate to greater than 2 times the actual signal's frequency, your acquired signal will accurately represent the actual signal's frequency. If you set your NI DAQ device's sample rate to 10 times the actual signal's frequency, your acquired signal starts to accurately represent the actual signal's frequency and shape. The takeaway is this: you must sample at least greater than 2 times the maximum frequency component of your signal to accurately represent the frequency of your signal. And typically, you must sample at least 5 to 10 times greater than the maximum frequency component of your signal to accurately represent the shape of your signal. Now that we understand how to choose the correct sampling rate to acquire a signal, we will now acquire and visualize our signal using MAX. First, I navigate to our DAQ device under Devices and Interfaces. Here I see my device. To launch the test panels, I need to click this button from the top command line of the window. This is where I can run the acquisition and view live data. Let's look at analog input. I'm selecting AI0 because my temperature sensor is connected to the AI0 channel of my device. I click here to begin the acquisition. As I touch the temperature sensor, the voltage increases. When I let go, the voltage decreases. Using these controls, I can configure channel and measurement-specific settings for my test panel. I can also set the sample rate. Right now, the test panel is auto-managing the timing and has set the rate. If I change the acquisition mode, for example, to continuous, it will give me an option to manually set my own sampling rate and samples to read values. Click this button to stop the acquisition. Now switch to the Analog Output tab of the Test Panels window. Here I can configure the signal mode and select which channel, for example, AO0 or AO1. And I can set the minimum and maximum range that I expect to output on this channel, and set whether to output a constant value or a sine wave. I'm going to leave this set to a DC voltage value. Here is where I can set the constant voltage value to output. To start actually updating the voltage that this analog output channel generates, I need to click the Update button. Now I'll switch to the Digital I/O tab for a digital input-output channel. On this tab, I can select the port, for example, port 0. A port is a collection of lines. Each line can output a high or low voltage. In the Select Directions section, I can choose whether to acquire or generate data. Let's select All Output. Here is where I can set whether to output a high or low voltage. To start actually updating the output that this digital output channel generates, I need to click the Start button. Now this channel is outputting the voltage that I specified. Finally, I'll set my final update to all low voltage, and then stop and close this test panel. If you see unexpected results from your DAQ device, try checking the following. Do you have the correct terminal connection selected? Are you using the appropriate sample rate? Is the channel configured correctly? Refer to the Field Wiring and Noise Considerations for Analog Signals white paper for more information about troubleshooting signals. Here's a summary of what you've learned in this lesson.